So it's going to depend on our situation. I just did something goofy. Sorry, guys. Just somehow hit undo. Okay. So here's what we're going to try first. We're going to try to draw NH3, which is called ammonia. Does anybody know what ammonia is in your house? It's in cleaner, yes. So it smells like cat pee. It smells horrible, right? If you ever smell cat pee is mainly ammonia. Your urine is also mainly ammonia. It's nitrogen excretion from your body because you don't need all the nitrogen you need. So that's just a fun fact. But NH3 is our compound we want to draw. So V means what? Valence electrons. So I need to count the valence electrons that NH3 contribute to the bonding situation. Nitrogen is in group what? 5. So it has how many valence electrons? 5. So we say 5 valence electrons plus the 3 from our 3 hydrogens, which each carry what? 1 each. Okay, so it gives us a total of 8 valence electrons. All right, who's going to be my central in my skeleton? Why nitrogen? Because there's some rules you wrote down on your sheet from yesterday. You have to select the central by looking for the, okay, was that the first thing listed?
Usually carbon.
Okay, so usually carbon or the singleton. The singleton means the one you have one atom of. Well, in this case, I got 3 hydrogens, 1 nitrogen. Nitrogen is a singleton. So I put an N in the middle, and then I'm symmetrically going to add on the rest of the atoms. These are called ligands. Ligands are the attached atoms. Okay, so I'm attaching hydrogen left, right, and down. You could have also put it up. It just needs to be as symmetrical as possible. H is all the way around. All right, what does one line represent? 2 electrons, right? If you guys can't see, remember, so the lab station, like there's a C right here, okay? So there's 3, so 2, 4, 6. 6 electrons have been used so far. So I need octet on everybody, right? Who needs octet currently here? Nitrogen. Okay? So now I'll put 2 lone pair. That's called a lone pair. Because I'm not bonding it to anything. So these lines represent bonded electrons, where the little dots singly by themselves are the lone pairs of electrons that are not bonding. Okay, so who has octet? Nitrogen. Who doesn't have octet, it's okay? Hydrogen. Okay, so I'm looking, I don't need to repair anything, it looks like. Everybody's got octet, we're fine. I need to review and recount. So when I recount these electrons, how many do I have? 2, 4, 6, 8. Check. I'm happy because I met my initial requirement. So guys, that's the structure. Okay, let's do the next one. CCl4. You go. You can do this. You probably need a periodic table out at some point today. How many valence electrons do we have, guys? 32. So carbon has 4, plus 4 times how many from chlorine? 7. So that's a total of 32. Who is in the center? Carbon, because it's the one that likes to share. Carbon's not so electronegative, it won't share. So it's fine to give a bond to everybody who needs it. So carbon's in the middle. How did you put the chlorines around? Where did you put them? So left, right, north, south. Okay. And what are these attachments called again? Say again? Ligands, because those are like legs. Think of it like that. So those are called ligands. Now, who has octet? Carbon. Who does not? So what do? How do I add electrons? Lone pairs, right? Dot, dot, dot. So they come in pairs, lone pairs. So that's why we've got 6 there. Plus that one bonded pair is 8. Dots, 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 dots. And lastly, we have 6 electrons around the last one. Okay, so now everybody has octet, right? And let's count. 8, 16, 24, 32. How many was that supposed to have? Yay! That's kind of a check mark to make sure we review. So, count valence electrons, get a skeleton going by choosing the central, adding everything else to the central. Give everybody octet. Consider if you need a pair back up, but we haven't had a situation with that yet. Review. That's your flow, okay? This is called VSEPR, VSEPR theory, and I use this acronym because we'll talk about the VSEPR theory in just a couple minutes, but it means valence shell, right? Valence electrons, valence shell, electron pair repulsion theory. We'll talk about why those repel. Okay, let's do 2 more, and then we're going to build some, like little chemistry Legos, okay? Can I go past this?
Yeah.
Yes? No?
Yes.
Yes. Okay. All right, so let's do, hold on, I don't want to do either of those right now. Let's do nitrogen. Try your best. I should have almost enough for everybody. Thank you. All right, Ariane, how many electrons does your table agree that N2 has? How many? 10. Good. So that's 5 plus 5, right? So that's 10 valence electrons. All right, guys, how did you choose a central? There's not really a central, right? There's not a singleton. There's no carbon. There's no largest. This is the same thing. So how do you have to attach these? N bonded to N, right? So there's really no question. It's not fishy. It's just N bonded to N. Now, if I give everybody octet, first thing I do is I go, okay, you need 6. Okay, 2, 4, 6, 8, check. You need 6 more. 2, 4, 6, 8, check. Looks like I'm done, right? Everybody's got octet. So now I need to consider reviewing it. So how many electrons are here? Yeah, 2, 4, 6, 8, 10, 12, 14. Well, I can't have more than 10. So here's where I revise. So when it says review, recount, we might need to revise here as well. Didn't really say that, but that's why we recount. If it doesn't mean we have to revise. And I'm now going to go back up and say, okay, did I need to pair something up more? Because essentially what I've done is I've given this nitrogen a lone pair and this one a lone pair. What could I make them do? Share, like have a share bond, a shared bonded pair. So when I take those 2 away, 2 lone pairs away, and I make it share with another bond, I've now made a double bond. Okay, so I'm moving in the right direction. Because now how many electrons do I have? 2, 4, 6, 8, 10, 12. Moving in the right direction. So what should I do again? Make them share again. So I'm erasing your lone pair and your lone pair and saying you guys have to share. Now I've made a triple bond. So this is an interesting situation because I actually had to erase some and revise and erase and revise. But that's your tool. That's your set of tools that you need to use. So we now have a triple bond. Super, super strong bond. Okay? All right, so we're going to talk about geometries and we're going to build. But before I talk about geometries, let's build these 3 that we just drew. Send me 1 or 2 people from your table. grab some more. Alright, come on. Open it up and don't start building without me.
Whoa, TJ, chill out.
Alright, so here, let's go back to the very first one we drew. And you gotta be quiet for me. There is a color code. There is a color code to this, but I'll tell you the color code out loud. The blue one is nitrogen. Pick up the blue B if you want. You guys all can build one. There should be enough there for everybody to build. And if you don't have some extras, I just haven't opened them yet. And the white ones are hydrogens. Build your structure. The white ones are hydrogens. Build your structure. Use the long, skinny, flexible, lives. Short, steady bond. Nitrogen, we're building the structure. Short, steady bonds. Those are your single, short, steady bonds. They're probably short, stubby, not the little white ones. Short, stubby, big ones. But you know, whatever. Tomato, tomato. It'll work out. But I'm going to try to get you guys using the right pieces. The white ones are not gone. I'm sorry, we're doing this all together, so I know some people are ahead. These babies are wicked hard to get in here to do. Okay, so the white beads are the hydrogens. The gray little short stubby bonds are single bonds. And you end up with a structure that looks like a, with a name. It's geometry, guys. It's not just a triangle, because a triangle would be a flat 3D. Look at it like that. Pyramid. Good. Now, what kind of pyramid? Triangular pyramid. You have to hold it so I can see the little triangle part and the pyramid part. Hold it like this. Does everybody see the triangle pyramid?
Yeah.
Okay, so we are going to go ahead and write down next to our structure. We're going to put the whole name here, okay? So it's called trigonal, fancy, trigonal pyramid, or trigonal pyramidal. Okay, so we have now decided that, how many ligands is this?
3.
Okay, so you guys are saying 3 ligands. And we're looking at the central atom of this, okay? The central atom has 3 ligands and what? One lone pair. So if you have 3 ligands and 1 lone pair, you are what shape?
Okay.
Triangle pyramid. You are not a fidget spinner, please. Thank you. Okay. Now go ahead and build, so deconstruct and build carbon tetrachloride, which is the second one we drew. Carbon is black. There's a cheat sheet in your thing. Carbon is black and chlorines are green. Carbon is black and chlorines are green. There's probably enough greens. No promises on that. Do not mix up these kits, by the way. If you're still from one kit, you put it back in that kit. Do not put it like in multiple kits, okay? We have counted all these beads, and I will hunt you down to make sure you distribute. But is it correct? If you don't have enough little green ones, it's fine. Use the white ones. Just take them from the same kit so you're not mixing up. Hold it up when you're done. High and proud. Hold it up. Okay, so this one, think of it like a prism. Think of geometry, okay? Think of it like a prism. If it had a face and a face, and a face, and another face, what would that be called in like geometry? Nope. Think in geometry, guys. 4 faces. Tetrahedron? Did you guys not do that in geometry? Well, now I'm telling you. Does anybody know what tetra refers to? Like, we are tetrapods. We have no, we are bipedal. We walk on 2 feet, but we are tetrapods. We have 4 limbs. Okay, tetra means 4. Okay, so write down next to this structure. Write down next to this structure in your paper. I'm waiting for you. Okay, tetrahedral, like a tetrahedron. Tetra means 4. If you forget that, write down that. Now, why are we putting tetra 4? What does this thing have? 4 ligands. Put the tetrahedron down, please. 4 ligands and 0 lone pairs. So what I've started with you with is like visualizing and thinking, oh yeah, this kind of looks like a pyramid. Oh, it's got 3 legs. It's a prismal pyramid. I thought maybe you knew tetra meant 4, but I was my mistake. So that's why this is called a tetrahedral structure. Go ahead and look at the little sheet that Ryan just passed out, which is the same sheet you had yesterday, and match up the 2 that we just did. Look at my cheat sheet on the bottom. You see the geometries? So if you get this chart on the test, you have no excuse, right? You should be able to figure out what the shape of something is based on counting ligands and lone pairs. Cool? Okay, let's do the last one that we just drew. Yeah, deassemble, deassemble. And while you're deassembling, I'll tell you this. Caveat this one. Real short, stubby bonds are for single bonds. The long, flexible ones are for multiple bonds. They could be the double or triple, like in this situation here. The long, flexible ones. There may not be enough in your kit for everybody, so share. So if you just put 1 long, flexible bond, you are wrong, because that is still only 1 bond. Make it work. You'll figure it out. Try for a second.
Oh my gosh.
Ryan, what do you do?
3.
You did 3. Why did you put 3 flexible bonds together? Because it's a triple bond. And you still have to make it mimic what it looks like. They're flexible. They can move. They can bend. Okay, hold up your triple bonded nitrogen. Okay, so look up here for me. Corbin, get you your triple bond, buddy. Triple bond. All right, make sure your neighbor has a triple bond, okay? All right, so eyes back up here for me. Put the triple bond down. And let's look. Now, this shape is not going to be on your chart, but use your common sense. You got a dot and a dot. It's connected. What kind of shape is that? Look at that. A line, which we're going to call linear. That is a linear structure. It is a line. It is just a little flat thing with 2 atoms in it. So this is linear. Okay, so we're going to work on, so we have a lab where we build, it's called a molecular modeling lab. We'll do this basically all day tomorrow. But I need to make sure you are comfortable with drawing the structures before you start building them and assign names and all that stuff. So I'm going to pass these out. We're going to work on this for maybe 10 minutes for now. Please pass these back, guys. Deassemble and pass these back, please. Extras all Once they are deassembled, please close the lid so I know you're with me. Put on the back. All right, guys, so let's process we're going to process the first one together, okay? And we'll take a couple more notes here in a second, okay? So CH3Cl. Here's the very first, what I'm expecting is you can do the first couple of columns. So 1, it says bond polarity, 2, electron dot structure, 3, molecular shape. I'm expecting we can go across the board and do these. So here's how I would start. I would start with drawing the structure, okay? And it's simply because it's a little easier. Does everybody have a paper? Yes, okay. It's a little easier to start with the structure. So CH3Cl, what's my first step in every single structure I draw? Valence electrons. So carbon has? Nope. Because it's in group 4 plus hydrogens 1, 1, 1. Okay, so there's 3 of them. This is on your paper and this is tiny. And then chlorine 7, so that's a total of 14. So put 14 VE so you don't forget how many valence electrons you just counted. And then next step V. So we're making the skeleton, but we have to choose the central. Who has to be central here? Carbon prefers to be central. Okay, and then what do I do the rest of them? Anywhere, yeah? So maybe top down, top or left and right. We want to make it symmetrical as we can. So we got 3 carbons and a chlorine. So I can't make it too symmetrical because I got a 1 row chlorine here. But hydrogen, 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 chlorine. Your chlorine could go in a different location, no worries. All right, so I've gone through the S, so I've gotten to the skeleton. What's next? Add electrons into octet. Who already has octet? Okay, and hydrogen has its own version of octet. So then chlorine needs what? How many? 6, 2, 4, 6. And so we are done with our skeleton. We've added electrons. I need to either maybe add more pairs, maybe not, but let's review it. So I have 2, 4, 6, 8, 10, 12, 14, check. That's how many I needed. I'm good to go, right? All right, so we've done electron dot structure. Now, the bond polarity, which means if you must use the electronegativity chart, is going to be a little tricky. We have a couple bonds here. What are the bonds present? Between what and what? Hydrogen and carbon. Okay, so H and C are one bond we must consider. So write H-C. If it's too small, you've got the back of the paper. I've just tried to print it so you guys had what you needed. All right, so I'm expecting everybody's with me. We're in the bond polarity, you're in HC. Look at the bond look at the electronegativity value for hydrogen. What is it? 2 point what? 2.1 for carbon. 2.5, that difference is 0.4, and your job is to label it as nonpolar covalent, polar covalent, or ionic. Polar covalent it is, but PC, just for, so we recognize that as polar covalent. And what's the other bond here? Carbon to chlorine bond, right? Because the carbon and hydrogen bonds are the same. Oh, sorry, go back up here. If it's polar covalent, I must draw a, what's the arrow called? Dipole moment. Who's it going to point towards? Carbon, right? So I'm just going to draw it up here, and I'm going to superimpose that on my structure. Now it's going to get sloppy. It's going to get messy. You don't have to do it for every single structure, but your job is to think about this because it matters on this next part, which we're going to talk about a little bit later. Okay. So I'm going to draw an arrow just pointing towards carbon, an arrow pointing towards carbon, an arrow pointing towards carbon, just to help me see the electrons are being pushed from hydrogen to carbon, from hydrogen carbon to hydrogen to carbon. So I've got like just carbon is more electronegative than hydrogen, which is what that means. Okay, so that's only one of them. What's the other bond? Carbon to chlorine. And I'm just gonna do mine like over here because I'm running out of space. So carbon to chlorine. Number for carbon is 2.5. Number for chlorine is 0.0. 3.0. That difference is 0.5. Is that polar, nonpolar, or ionic? Polar covalent. What must I draw? Pointing towards chlorine, pointing towards chlorine like that. And so I'm going to do that over here as well. So do mine on top of the bond because mine's really messy already. Okay. Yep, there it is. Carbon to chlorine. We'll talk about why that matters later, but I just want you to superimpose those. All right, so check, we've got bond polarity covered. Check, we've got electron dot. Molecular shape. Can you tell me this has a central atom with 4 ligands? What's the shape? And do you have to look at your sheet for that one? If you know it, you know it, okay? But check your sheet just in case. Yes. Excuse me? This one goes in this box here. I just ran out of space. Yeah, there's 2 bonds right. All right, now I would recommend you go ahead and draw a bunch of structures. Okay, take some time right now and then ask me some questions. Because there are going to be some exceptions for rules in just a minute. Try to do some of the easy ones that you feel comfortable with. So I should see you drawing structures, and since you have your electronegativity sheet in front of you, you can check your bond immediately. Because let's say you drew it covalent, then you check and you're like, oh, it's ionic. You can't draw it the way you drew it. Phew. Has anybody seen a problem with the second one? What's the problem? It's ionic. Can you draw with the line between the BA and the O? No. Remember how we drew ionics yesterday? You might need to look at your notes from yesterday for just that one. That's the only one that's ionic. I've tricked you on the second one. the one you're on. I just want to show you one caveat. Finish the one you're on. And I'm putting this reminder on the board for you for two things here. Eyes up here for the moment, okay? Just maybe a minute. If you end up with, everybody has octet, and you're like, oh gosh, I've got 2 electrons left, what do I do? Or I've got 4 electrons left, what do I do? If you have extra electrons and you add them to the central atom, just as lone pairs. You wrote this down yesterday, yes? Some of you guys didn't get quite to the bottom of this, but that was what we wrote down. And there are some electrons, which, sorry, I'm doing the same thing in AP Chem right now. I was with you guys. Did I mention expanded octet yesterday? Meaning can go past 8. Okay, so that's a thing. Remember I told you the octet rule was kind of a rule. It's more of a suggestion. Duet's one of those exceptions. Expanded octet is also an exception. So it starts with phosphorus. So look where phosphorus is on the periodic table. Phosphorus, sulfur, chlorine. Okay, phosphorus, sulfur, chlorine. And basically down from that, they can expand octet, meaning they can have more than 8. They can have 10, 12, 15, 16, okay? So, and the reason is because they have access to 3d orbitals. Because phosphorus, look and see what group, or what period it is in. What is it? Group 3, right? Well, that's 3p right there, right? Well, if I'm in the 3rd period, I still have access to other orbitals, even though I don't need them. Like phosphorus only needs up to 3p, but 3d starts right there in that group, in that d block. So phosphorus has d pockets it can fill, like 3d pockets. So that's why I can expand octet. Okay, go through the xenon example. I'm gonna leave that there. I'm gonna try a couple more and we'll pause. Yeah, that's one. First, because if not, you won't be able to check them at the end. So a lot of you guys are writing them down. So I want you to consider looking, once you finish the first, the left-hand side of the paper, look at the molecular geometries now for all the ones that you've done, and check it on the paper. Now, you're going to have to question yourself on some of them because some of the geometries you just can't see until you build it. So you physically build it. So when we build them tomorrow, you might revise some of those geometries based on what you see. Because you'll find one, I think the xenon tetrafluoride or XeF4 is not on paper, and you can't see it until you build it. So I put a big old question mark there, because I'm not going to tell it to you. I've given you guys some exceptions so you can see more. Take one more minute wherever you are, okay? One more minute wherever you are. So this is a, good? I'm going to cut the lights on a second if you didn't get a picture yet. You'll have plenty of time, okay? So thanks for getting logged on. You put your lab sheet up for me. So on your notes, wherever you were just writing down some information, it's going to explain what the VSEPR theory is and what determines the shape of the molecule. I'm going to elaborate after this video, okay? So I would have my stuff back out for you.
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. And its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged, and electrons are negatively charged. And if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of 1 carbon and 4 hydrogen atoms. But it doesn't tell us what's bonded to what, or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to 4 other atoms, and that each hydrogen can only bond with 1 other atom. So, we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now each bond represents the sharing of 2 electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge, and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this.
What's the shape?
This is called a tetrahedron.
Good job, guys.
Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid. Carbon dioxide, or CO2, is a straight line. Water, H2O, is bent, like your elbow would be bent. And chlorine trifluoride, or ClF3, is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't. Now, shapes get more complicated as you increase the number of atoms. All the examples we just talked about had one obviously central atom, but most molecules, from relatively small pharmaceuticals all the way up to long polymers like DNA or proteins, don't. The key thing to remember is that bonded atoms will arrange themselves to maximize the attraction between opposite charges and minimize the repulsion between like charges. Some molecules even have 2 or more stable arrangements of atoms, and we can actually get really cool chemistry from the switches between those configurations, even when the composition of that molecule, that's to say the number and identity of its atoms, has not changed at all.
Alright, so we said, remember the main, we mentioned like there's a central atom and then some are like DNA and they're huge. What was the main goal here? Atoms in a molecule, what do? So they arrange themselves so they have maximum attraction between like or unlike things and minimum repulsion. So we don't want things to be super, super repulsive because that's really, really unhealthy and unstable for a compound. So we follow the VSEPR theory. So write down VSEPR, VSEPR. Which is what we've been doing this whole day, by the way. We've been building these molecules, and they've arranged themselves in such a way that the atoms are spread out as possible. So we've been following these rules, but let's know what it means too, okay? V means valence, shell, electron, pair, repulsion. Valence shell, electron pair, repulsion. Valence shell, electron pair, repulsion. So that's just a big theory that essentially says these two things, and this is the only other thing I'd really write down right now. It helps, one, predict the 3D shape. Okay, so those are all the geometries, you know, tetrahedral, trigonal planar, trigonal pyramidal, and some others that you're not going to know yet because you have to build in first to see them. So it helps predict the 3D shape, and the way that we predict the 3D shape is we look to see how electron pairs are repelling. So those lone pairs, and this is kind of this third bullet here, the lone pairs are really pushy, they're repulsive, nobody wants to be near them. So put your arms out straight like this, try to hit your neighbor, okay? If your head is a big, huge lone pair, that lone pair does not want to be, look up here, okay? That lone pair does not want to be close to this bonded pair. So what is the lone pair going to do to the bonded pair? So it's a negative and a negative. What does negative do? Repel. So what happens to your arms? They go down. Well, now what shape are you? You're not a penguin. What shape are you? You're bent. You are a bent shape. Okay, so basically what you should know, it helps predict the 3D shape because the lone pair push the ligands together. And that alters the shape. It alters the 3D shape. So finish writing down what you need to. And then you should be on my website hopefully very soon. You know, it's generally our goal in life. If you guys would stack the kits and the EN sheets, that would be helpful. Pass this around. Alright, so you've stacked the kits and the EN sheets on top of the kits. Just I'm trying to give you guys some space to work with. And everybody, give me a thumbs up when you have your set molecular shapes VSEPR activity. You're on my website. I'll show you where this link is under homework. I do try to link a lot of, I think I put the link there, I say that with confidence. The link is also here on the paper. Here it is. Extras.
We're too short.
Okay, I'll get you guys in just a second. So when you go to the PhET molecular modeling link, which let's verify, is that on my website? Did I put it there? Okay, well you've got the link right in front of you. I swear I put it there. Apparently I lied to you all. It is, and where did I don't. No, that's molecular polarity from yesterday. So go to the link on your page, on your worksheet. If you just Google PhET molecular shapes, it should pop right up. PhET molecular shapes. PhET molecular shapes. PhET molecular shapes. One more time. PhET molecular shapes. Not the other one. Okay, and now you guys can begin. You guys can see the instructions with me. How to treat this. Here's about what you needed. PhET molecular shapes. One more time. I see Google polarity select. Google PhET molecular shapes. I still see you're not there. Thank you. All right. So you guys have what you need. If you need me to answer some questions, I can. But you'll notice this is click on. There's your intro. It tells you how to start with the generic molecular geometry. It tells you how to draw. And I want you guys to try your darndest to see if you can visualize these shapes as you go. Because tomorrow we will build. Feel free to talk to each other. Do what you gotta do.